Problem 4. For a steel alloy, it has been determined that a carburizing heat treatment of 10 hours duration will raise the carbon concentration to 0.4 weight% at a point 2.5 millimeter from the surface. Estimate the time necessary to achieve the same concentration at 5 millimeter position for an identical steel and at the same carburizing temperature. So this is again a non-steady state diffusion problem because you can see that the concentration values are changing with time and position. So for non-steady state condition, we know that this equation is valid. So concentration at any point x minus the initial concentration at the same point divided by the surface concentration minus the initial concentration is equal to 1 minus error function x over 2 under root dt. Okay, so now apply this equation to this condition. Okay, so for the first case, firstly we have this situation, 10-hour time and a concentration was achieved 0.45 weight% starting from some initial value and maintained at, and it is assumed that surface concentration is maintained at Cs. So Cx will be 0.45, C naught we don't know, okay, and similarly Cs we don't know, C naught is here, it is equal to 1 minus ERF. X is the position which is 2.5 millimeter from the surface, so 2.5 millimeter, so you can represent it into meter, although it is not necessary in specifically in this problem, as we will see later. And 2, and d is the diffusion coefficient, we also don't know, and t is the time, in 10 hours. Okay, so we can take it as in seconds, so it's like that. So this is this first condition. In the second condition, it is said that estimate the time necessary to achieve the same concentration, same means this 0.45%, at another point 5 millimeter position. Okay, so we can apply this equation again, same concentration between 0.45 minus C naught. C naught will be the same because in the initial condition, at time 0, at the beginning we will assume that all concentration throughout will be same, so same as Cs minus C naught. Okay, and this is equal to 1 minus ERF to 5 into 10 to the power minus 3 divided by 2 into d t, because we don't know the time, we need to find the time. So now, okay, now comparing these two equations, so this, you can see that this left hand side of this equation is equal to this, are the same, one is same as here, and well, the argument inside of this error function should be also same. So for example, then if we will equate it, then simply we can equate these two arguments, okay, so of ERF. So ERF we don't need to, I can simply say that I can cancel out this, cancel out this, cancel out this negative, cancel out this ERF, although it's not a scientific way of cancelling it out, but first we need to equate them and then subtract these things. Anyway, so now we know that 5 into 10 to the power minus 3 meter is equal to 2 under root d. T is equal to 2.5, okay, into 10 to the power minus 3 over 2 under root d, and then you can see that more things are cancelling out. This cancels with this cancels with this, and under root d will cancel out with under root d. So what is left? So many cancellations. So 5 is left here, and under root d is left here. I think I'm making some mistake over here. Yeah, for 2.5 it was not under root d, it was this, okay, it was this, so it was 3600 times 10, 36,000, okay, 36,000, okay. So 5 over under root t and then 2.5 over 36,000 square root. Anyway, so now you simplify it, so it will be 40 hours. The time will be 40 hours. If you find the time in seconds, so you can convert it back to hours. So this will be the time. So that's the answer.